Math 1314, section IC1. Spring 2022, Tyler Junior College, section 1.5, Linear Inequalities, video 4, Double Inequalities. This is actually just a compound inequality, and specifically an AND inequality. I'll show you what I mean in the first example. Solve the inequality. -5 is less than 7x plus 2, which is less than or equal to 23. This is really just an AND inequality. The first inequality is -5 is less than 7x plus 2. And the second inequality is 7x plus 2 is less than or equal to 23. But they can get merged into a double inequality for two reasons. Number one, the inequality symbols point the same direction. They are both less thans. Granted, one of them is less than or equal to. And number two, the right side of the first inequality is exactly the same as the left side of the second inequality. In such a case, the inequalities can be run together to make a double inequality. So how do we solve this? Well, technically, we could split it into the two inequalities it represents and treat it like an AND inequality, solve them separately, find their individual number lines, and then find their intersection since it's an AND. But if you think about it, solving both inequalities would involve the exact same moves because both of them involve 7x plus 2, which would require the same moves for isolating the x. So instead of splitting this into two separate problems, we can work it as one gigantic problem. Our goal is still the same. Isolate the x in the middle, but we have to make a slight change to our flow. Normally, when you solve an equation or an inequality, you follow the rule, whatever you do to the left side, you do to the right side. But in a double inequality, there is more than a left and a right. There's a left, which in this case is just -5. There's a right, which is 23, and there's a middle. So now instead of saying whatever we do on the left, we'll also do on the right, we're going to say whatever we do in the middle, we'll also do on both the right and the left. Keep in mind that we are trying to get the x by itself, so our moves are dictated by getting the x by itself. Our first move is going to be to subtract 2 from the middle, but whatever we do in the middle, we have to do on both the left and the right. On the left, we get -5 minus 2, which is -7, is less than. In the middle, the 2's cancel, leaving a 7x less than or equal to. And on the right, we have 23 minus 2, which is 21. Continuing to get the x by itself, our next move is to divide the middle by 7. But whatever we do in the middle, we have to do on both the left and on the right. As a result, on the left, we get -1. In the middle, the 7's cancel, leaving an x. And on the right, we get 21 over 7, which is 3. So our solution is -1 is less than x, which is less than or equal to 3. 1 second, folks. All right, I had to pause briefly. So how do we represent this solution as both a number line and an interval? Well, it's actually pretty easy. If we take our solution, which is -1 is less than x, is less than or equal to 3, the number line is really easy to draw. If I could draw it straighter, that would be even better. Why don't we do this? The number line is really easy to draw. All you have to do is shade between the numbers that the x is between. In other words, the x is between -1 and 3, so we're going to shade between -1 and 3. Now, we still use the same protocol for brackets and parentheses. Because it says -1 is less than x, as opposed to less than or equal to, we would use a curved parentheses on the -1. Then we would shade over to the 3. And because it says x is less than or equal to 3, we would use a square bracket on the 3. So what's our interval? Well, from left to right, it is shaded from -1 to 3. So our interval is parentheses, -1, comma 3, bracket. Pretty easy to finish. There's only one small thing you need to be on the lookout for, and this example will illustrate it. Solve the inequality. -4 is less than or equal to 1 minus x over 2, which is less than or equal to 6. Again, our goal is still the same, get the x by itself in the middle, but whatever we do in the middle, we have to do on both the left and the right. Because the middle is over 2, aka divided by 2, our first move is to cancel the divided by 2 by multiplying the left, the right, and the middle by 2. On the left, we get 2 times -4 is -8, less than or equal to. In the middle, the 2's cancel and leave 1 minus x, less than or equal to. And on the right, we have 6 times 2, which is 12. Continuing to solve for x, we're going to subtract 1 from the middle to cancel the 1, but then we must subtract 1 from both the left and the right. The results, on the left, -8 minus 1 is -9, less than or equal to. In the middle, the 1 and the -1 cancel, leaving a negative x less than or equal to. And on the right, we have 12 minus 1, which is 11. We'll pause this, move it up just for a second. There we go, a little bit of room below it. Why do I need room below it? Well, because the x is not yet by itself, it has a negative in front of it. And I'm not sure if this phenomenon has occurred in prior videos, but if you have a negative on an x, the best way to think about getting rid of it is to think of it as -1 times x, because then you're just undoing a multiplication move. We're going to divide the middle by -1 to cancel the -1 on the x, and then also divide both the left and the right by -1. But why is this troublesome? Because of the rule, if you multiply or divide both sides of an inequality by a negative, you have to reverse the order of the signs. So not only am I going to do all the division, all of the less than or equal to's are going to get turned around. So what's the result? The result is this. -9 divided by -1 is 9. You might hear my dog in the background. The sign does get turned around because we just divided both sides by a negative. In fact, let's go ahead and turn around both of them. In the middle, the -1's cancel, leaving the x. The second inequality gets turned around to read greater than or equal to. And on the right, 11 divided by -1 is -11. Let's move this to the final page. 9 greater than or equal to x, greater than or equal to -11. Now, there is absolutely nothing wrong with this answer. However, to me, it's backwards. When I have a double inequality, I like for it to go from least to greatest as of the number line. So how can we accomplish this? By literally turning the whole thing around. Saying that 9 is greater than x is the same, greater than or equal to x is the same as saying x is less than or equal to 9. And saying that x is greater than or equal to -11 is the same as saying -11 is less than or equal to x. So literally turn the whole thing around so that everything is going from least to greatest instead of greatest to least. Why? Because when we draw the number line, the lesser number is on the left, the greater number is on the right. To be honest with you, it is not essential to reverse the entire solution so that it goes from least to greatest. It just makes it more consistent when you draw your number line. And speaking of your number line, because the x is between -11 and 9, we're going to shade between -11 and 9. And because both of the inequalities say less than or equal to, we'll use a bracket, a square bracket on both numbers. Square bracket on the 11, shade to the right, square bracket on the 9, making the final interval solution bracket -11, comma 9, bracket. So solving a double inequality, pretty easy. The only thing you really have to watch out for are the instances where you do one of the two moves that causes the entire inequality to reverse. In this case, that move was dividing by a negative.